big services. So we would have a syncing microservice in the middle that was responsible for looking at change events on one service and then taking that data and updating it in the other service, and sometimes going backwards again. So this worked really well for this use case. It was small amounts of data, it was kind of like a drip feed, it was all nicely abstracted, and it worked well. So because that worked well in this scenario, when we came to a different scenario, which was syncing very large amounts of data between two systems, because we had our hammer, we were like, okay, so we're going to keep using this hammer for this problem as well. Unfortunately, this was the wrong tool. With the very small amounts of data, it's just one HTTP request to get and then another to put in the other system. When you have the large amounts of data and you're trying to use JSON, don't go to sleep. You end up having to do paging, and then your service in the middle has to know which page it's up to, and it gets very stateful and messy. And even though we tried to think of a way around it, because we still were using our hammer, we were like, oh, okay, we'll just make it work. And we did make it work, but it wasn't a really elegant solution, and nobody really felt really happy with it. So the thing about this data was, it wasn't actually fresh data anyway. It only got updated once a day. And if it hadn't been the live data, it wouldn't have mattered. So there was no real reason for it to have to be a dynamic service. Just keep that in mind for a second. Batch processing is a tool that we all know about and we've all probably used, but it's not really cool. It kind of has this legacy of scripts running on a box somewhere and having messy file permissions and sticking stuff in folders, and it's not modern and it's not cool, and it doesn't have a history of being well tested and like loosely coupled. The things that we like about our little microservices, our abstractions and our hypermedia, we don't really associate generally with batch processing. But what I want to talk to you today is about how we can take things that we like about the microservices we're making now and get the advantages of batch processing along with that. So at REA, they're pretty keen on their Amazon Web Services, and they're keen on their microservices. So along with some people from ThoughtWorks, they developed this concept of Hipster Batch. So Hipster Batch takes batch processing and AWS and REST with Hypermedia and metadata and smooshes them all together to make something that is actually quite fun to do. So REST is a representational state transfer, which is based on the old concept of HTTP verbs. So the get and the put and the post. And because we all write dynamic services these days, we kind of always think about resources as being dynamically generated, and I know I did. But there's actually no reason for those resources to be dynamically generated on the spot as you request them. They can quite easily be pre-generated and sitting there waiting for you to request them. You think about the old HTML pages, like put and post and get were all about static files that lived on a web server somewhere. And we can take this concept and apply it to our hypermediarized batch processing. So let me walk you through how we implemented our Hipster batches. So step one was we used an AWS Autoscaling group, and we said at a certain time we want you to scale up from 0 to 1. and we had a script that would automatically run the batch process when the instance was scaled up. So this kind of took care of our scheduling. And because we only needed them to run once a day, this worked fine. Obviously, if you had a more complex process, you need a more complex solution. So step 2 was to actually do the processing. So it could be an SQL query that you need to make, or processing some CSV files, picking up some information from any other system, doing the processing, and then generating an output. Now, step 3 is writing that output to S3 with Hypermedia Links to allow the files to be navigated by a consumer as if it was a traditional, well, a standard dynamic HTTP service. Now, if you're lucky enough to be using Ruby, this means that the code that would navigate your file structure in S3 can look exactly the same as the code that would navigate any RESTful service. So we could say open HTTP some service and then go to follow the hypermedia links, or we could say open S3 and then the file path and then navigate those hypermedia links in exactly the same way. This makes it really easy to test, by the way. Now, the key is for making a nice hypermedia system is to have relations that your consumers can navigate without actually having to know what the URLs of your resources. So this is what one of the index files would look like. So we were using help. You can see there we have the hrefs to the reporting data, the customer portion of our reporting data, and we have a relation to get all that data and a relation to get the latest of that data. Now, we came up with this concept of the data ancestry. Often, when we're taking data from a whole lot of sources, we lose track of where that data came from and exactly what data set. So this ancestry is designed so that in any downstream data set, we can always trace backwards to the data sets that it came from and work out if there's a problem here, well, this was made up of these data sets and that was made up from these data sets, so we can trace it all the way back to the source to see where the problems come from. It has metadata about the batch job itself, links to the data files, so links to the source files that we use to create the output, links to the logs, so we can we tag or we put a UID in the log for each batch job, so that we can then have a link that goes to Splunk and filters by that UID, so we can see all the logs for a particular batch job. And yeah, sometimes we upload the source data, and sometimes we just have a link to the source data. And so these ancestries then become nested within each other. If we use this to make another data set, we'd include this ancestry in that ancestry, and it all become very parental. So here's an example. Sorry about the big long JSON document. Here's an example of one of the ancestries. So the name of the service that created it was the customer collector. It's got the months that the data is relevant for, start time, the duration, the links to Splunk, and then down the bottom is the ancestry of the source data that we used to create this. So this is an example of a service that was picking up a CSV file that was emailed to Box by some business users. So that's why it has a Box href down the bottom. So we can always go back to Box and say, oh, well, this is where that file was. So the file structure is that index.json, And then we split our files up into three main sections: the Ancestry files, the data files, and the source files. This makes it quite easy if we ever wanted to go in and say, I want to get all the data files. We just have to list the data files in that directory. I would try not to expose that sort of information if we don't need to. So one of the quirks of this particular system was that we would be processing the customer information each day. However, the consumer of this data only wanted to know the latest customer data for any given month. So we would have a complete copy of the customer data processed for each day, but we always wanted to load the latest one. So to help the consumer, we gave it a hyperlink in our hypermedia structure so that it would always know the URL to the latest data for that month. So we had another directory called the latest by month, and we would every time we processed a new customer data set, we would put over that Ancestry latest by month with a copy of the file, of the Ancestry file that you see in the Ancestry directory. So it kind of behaves like a symlink. So there's an identical copy of the latest one at the latest by month and at the in the list of all the Ancestry. So it might make more sense when I show you the next step. So these bold ones are the files we've added the day later. And now our Ancestry latest by month is a copy of the second Ancestry file. And our index.json will, in its all relation, include a link to the Ancestry latest by month, so that every consumer who wants all the data only ever gets the latest data for each month. I hope that makes sense. So all this behaves like a dynamic system to the consumer. It's always getting the latest data. That latest by month is always being dynamically updated to all intents and purposes for the consumer, but it's actually static files. And rarely at any stage do we have to get a file, modify it, and put it down. It's all as idempotent as it can possibly be. So why is it cool? Compared to the normal batch processing that we've been familiar with, the security is the major factor of this. Using AWS allows you to use all the security policies that come along with all the AWS features. So it's much better than sticking a file on a shared drive somewhere that anybody could delete or move or tamper with. Using the hypermedia makes it really flexible. So if we wanted to change our underlying data structure, we could do that without upsetting the consumer in the way that we could change any hypermedia system. And auditability. Because we're using AWS, we have all the audit tools that come along with AWS and all the file logs and that Ancestry structure that lets us go, okay, well this file came from here and that was created by this person. So we have links all the way back to the people that are responsible for the data. So testing. If anybody's seen me talk before, it's probably unpacked. But Pact was specifically originally designed for HTTP contracts between consumers and providers. And in this instance, well, we do kind of have some HTTP, but it's buried many layers below the S3 and everything else. And we really don't care that it's what the communication protocol is. All we care about is the documents that the consumer and the provider are sharing. So the testing solution we came up with was to have a contract using the packed JSON declaration format. And our consumer has a test that shows that it can correctly handle the data that it expects. And we declare the structure of the data that we're expecting in just the same way that we would declare an HTTP pact of, when I make this request, I expect this response. And then we share that contract. We're using the packed broker, but you could share it via build resources or pushing from one Git repo to another, whatever works for your setup. And then in our provider, we have a test that shows that it can produce the data that the consumer is expecting. So this is exactly the same concept as the traditional HTTP pact, but the tests are run in a different way. So that's pretty much it. Quick talk tonight. Does anybody have any questions?
What do you do with batch jobs fail? What's the recovery methods?
Yeah, we had retries built in a few places. We had some issues with some database contention at one stage because we had a couple of services accessing the same database and we're getting some weird errors. So we built in some retries. The logs and the Ancestry had a status so that when the batch process failed, it would still try and write that S3 file. Obviously, if S3 was the point of failure, then you're not going to get that file. But hopefully you'll still get the Splunk logs. But yeah, even when they did fail, we'd still write that Ancestry. But we wouldn't, if the batch job failed, then we wouldn't update that latest link so that the consumers were still getting the good data from the previous day, which in our case was okay.
Do your consumers directly read from S3 or do you have something?
Yeah, so the question was, did our consumers read directly from S3? And the answer was yes. Yeah, we used that file read, so that just passing it the URL. We did try to abstract it with some hypermedia libraries, but the structure is actually so simple that we ended up finding it easier just to parse the JSON and write our own classes around that.
It was sufficiently performant enough to be no problem?
Yeah. S3 is S3.
Latency was slow.
Yeah, well, all our data was in Sydney, and that was fast enough for us. Yeah.
The packed packet, is that part of the normal packed bucket or something?
It's picking just the matching part out of the normal packed library. So the normal packed library, the bit that you interact with is generally the DSL of given this service, when I make this request, I get this response. But there's a matching portion of that library, and it just used the matching portion. There's an example, I'm trying to think where the link is from. I think there's a example on the packed wiki of how to use the packed matching library without HTTP.
With
Yeah.
non-production environments, if you use it to try and bring up systems to a particular point in time, resources and stuff.
So the question for video is, with non-production environments, did we try to use the system to bring up snapshots of previous data?
I'm just thinking of that use case for quickly go get a restore and bring it up to a week, a minute with a restore.
You probably could. We never really had that use case, but because it's kept every copy of the data, so you have the customer data at Monday, you have the customer data at Tuesday, you have the customer at Wednesday, I don't see why you couldn't. Yeah. Oh. If anybody's got any more questions, hit me up on Twitter, and I guess we're having a break now?
Yes.
Yes. So come and chat to me in the break if you like. Thanks, guys.